Okay, so in Sullivan's Calculus, Chapter 1, Functions and Limits, we are arriving at Section 1.3, New Functions from Old Functions. First objective, transformations of functions. By applying certain transformations to the graph of a given function, we can obtain the graphs of certain related functions. So, you got old functions, and then you're going to make new functions. This will give us the ability to sketch the graphs of many functions quickly by hand. That's big. And mentally, that's even bigger. It will also enable us to write equations for given graphs. So, we can go back the other direction. We can see a picture and write the equation, just as we can see an equation and see the picture. Let's first consider translations. If c is a positive number, then the graph of y equals f of x plus c is just the graph of the original y equals f of x shifted upward a distance of c units. So they could have said translated, but they said shifted. And they could have said shifts, but they said translations. And confusingly, there are many other words for this kind of transformation. Okay, it's a shift, it's a slide, it's a glide, it's a rigid motion, so lots of words for the same thing. So you add c and you shift upward a distance of c units because each y coordinate is increased by the same number c. Change all the y coordinates, you change the vertical components of each point, and therefore change the vertical component for the entire graph. Likewise, if g of x equals f of the quantity x minus c, where c is positive, then the value of g at x is the same as the value of f at x minus c. That is c units to the left of x. So here is g of x. G of x is f of x minus c, they're saying. So here's the g of x right here, this blue one. That's the washer. And let's just say there's an x. Okay, so right here, there's an x value. Could be any number. And they're saying the value of g at x, in other words, the height, right? That height right there, that's the value of g of x, whatever that distance is the same as the value of f, here's f, at x minus c. Well, if that's c right there, that distance is what we're calling c. X minus c puts us here, and the value of f at c is up here, and you can see that it's the same as the value of g at x. Therefore, the graph of y equals f of x minus c, which we're now calling g of x, which is the blue one, right? F is the black one, G is the blue one. Notice the c is on the inside of the parentheses. That's big. The graph of g, which is f of x minus c, is just the graph of f shifted c units to the right. Okay, so kind of the opposite of what we expect, right? Because you see that minus sign and you expect leftward movement, but actually we have rightward movement. Put them all in the if we if black box, black we can see that we've got a number c. The new one. We're saying it's positive, and we can add c to f of x on the outside of the parentheses. We could subtract c from f of x. We could subtract c from x on the inside of the parentheses, or subtract c from x, or add c to x on the inside of the parentheses. Okay, so now they're saying in order to make the new transformed, in this case translated or shifted graph, we apply these translations to the old one. Okay, here's the old. So to obtain the graph of y equals f of x plus c, shift the graph of the old one upward. If c is subtracted, shift the graph of the old one downward. If x is replaced with x minus c, shift to the right. And if x is replaced with x plus c, shift to the left. Okay, so it's good for these two to think about the transformation in the algebra as replacement. Replacement. X is being replaced by something. Now let's consider the stretching and reflecting transformations. Okay, so stretching and reflecting. This is not just a rigid motion. We might be changing the shape of the original graph. If c is greater than 1, then the graph of y equals c f of x. Now, that's multiplication right there. F of x is being multiplied by c. Is the graph of y equals f of x stretched by a factor of c in the vertical direction, because each y coordinate is multiplied by the same number c. So instead of, if you can imagine the table, maybe in the table the values in the y column are 1, 2, 3, 4. In the new table, they would be 2, 4, 6, 8. And now all the y values are bigger, and so you have a vertical stretch. The graph of y equals negative f of x, okay, so now it's actually f of x is being multiplied by negative 1. That's the graph of y equals f of x reflected about the x-axis, because the point xy is replaced by the point x negative y. Okay, so right, this is negative y right here, and that's the opposite of the old y value, meaning it is going to be on the other side of the x-axis. Okay, so here's a figure, and there's going to be a following chart where the results of other stretching, shrinking, and reflecting transformations are also given. Okay, so here's y equals f of x, this black graph here, and we are going to multiply the function. We're going to multiply f of x by negative 1, and that gives you this orange graph down here, and you can see how it's been reflected over the x-axis, so that you could imagine the folding over the x-axis lands the black graph on the orange graph. Maybe it looks brown on your computer, not quite sure. But there are other transformations also. In getting the orange, what I'm calling the orange graph, we're replacing y with negative y, right? We're replacing y with negative y. But what do you think? Okay, so if replacement of y with negative y reflects over the x-axis, what do you think that replacing x with negative x does? Well, if you replace x with negative x, you're going to reflect the graph over the y-axis. Okay? And get the blue graph. And we've already talked about the 1, 2, 3, 4 changing into the 2, 4, 6, 8, and a vertical stretch, which is always going to happen when we multiply our function by a number c greater than 1. But, what if c were 2, okay? Then every point on the graph is going to be, double the distance from the x-axis that the corresponding point on the original graph was. In this case, it looks like, well, maybe 3 times. I don't know. But if you were to multiply by 1/2? Okay. Well, what do you think is going to happen? What if your salary were multiplied by 1/2? Would that be a good thing? No, that would be a bad thing. Your pay would be half as much. And so every point on this green graph here is a half or a third of the distance from the x-axis as the corresponding point on the original graph. Okay, so this distance here is only a third of this distance here for c equal to 3. It looks like it's between 2 and 3. But then we can put it in words. Okay, so to obtain a new graph, we are going to take our old graph, y equals f of x, the black graph, and do some things to it. We talked about the multiplication by c's resulting in vertical stretch. Multiplication by 1 over c, vertical shrink. Okay. And we talked about multiply by -1, multiply your function by -1, that's reflection through the x-axis. Replacing x with negative x reflects the graph through the y-axis. So that's the black graph going to the blue graph in the picture on this slide. Now, in the middle, we have sneaked in, very innocently, these two transformations, which, by the way, happen to be the freakiest of all transformations. Okay? X is being multiplied on the inside of the parentheses by a number c. Okay? And the result is that the graph is shrinked horizontally. Okay? It's a horizontal shrink or a horizontal compression. And if x is being divided by c, or multiplied by 1 over c, same thing, right? You divide by 2, that's the same thing as multiplying by 1/2. Then you have a stretch horizontally. And so again, with the horizontal transformations, we have kind of the opposite sort of transformation that you would expect given the algebra. You see the multiplication, you're thinking something's getting bigger, but actually we're doing a horizontal shrink. You see the division, and you think something's getting smaller, but it's actually a horizontal stretch. And so here's an example. We have cos, the blue graph. I'm sorry, it's the pink graph. Okay, so y equals cos x, and that's the pink graph. Let's talk about these horizontal stretch and compression. Okay, now x here is going to be replaced by 2x. X is going to be replaced by 2x. Is that going to stretch or shrink horizontally the graph? Well, you think, oh, okay, well, we're multiplying by 2. It's got to be a stretch. But no, it's a shrink or a compression. We're going to get this blue graph, and that's the pink graph scrunched in toward the y-axis. Okay, so on the pink graph, we have a point. Let's look at this. Let's see. Okay, let's look at this x-intercept here at pi over 2. Okay, now pi over 2, that's half of 3.14 approximately, so it's about 1.57. After the horizontal compression, we now have a x-intercept less than 1. You can see here's 1. It's less than 1. It's half of that 1.57, so it's about 0.7 something. I'm sorry, yes, it's about 0.78 something. And so the corresponding point is much closer to the y-axis than the corresponding point on the original pink graph. Up here with the green graph, x is replaced by a half x. And you might think it should mean a horizontal compression, but it's a horizontal stretch. You can see that the green graph has been stretched way out, so that the new x-intercept is actually at pi, right? 1, 2, 3, pi. Double the distance from the y-axis that the corresponding x-intercept in the original pink graph was. So when x is replaced by something times x, you have a horizontal stretch or compression the opposite way that you expect. The opposite of what you expect. For instance, in order to get the graph of y equals 2 cos x, we multiply the y-coordinate of each point on the graph of y equals cos x by 2. This means that the graph of y equals cos x gets stretched vertically by a factor of 2. And we arrive at the blue graph in the first picture. Right? The blue graph in the first picture, vertical stretch by a factor of 2 because of this 2. This cos x is being multiplied by. Given the graph of y equals square root of x, use transformations to graph. And let's see, we've got part A, we've got part B, C, D, and E. And I want you to take a moment, maybe pause the video, and think about what is supposed to happen to the graph of y equals square root of x. I trust that you've memorized that graph of the square rooting parent function for a, b, c, d, and e. Well, when you subtract 2 from a function, you have a downward shift 2 units. When x is replaced by x minus 2 on the inside, you have a right shift. When a function is multiplied by -1, that's going to be a reflection over, which axis is it? The x-axis. When a function is multiplied by 2, it's going to be a vertical stretch. And when x is replaced by -x, right, reflection over y-axis. Okay, so there's your parent, the blue graph, and then we have part A, which is the downward shift by 2 units that we were talking about. Yes, the point 0, -2 is on that graph. And then the replacement of x with x minus 2 means that right shift that we were talking about. And okay, so we looked at this one, which was a downward shift 2 units of the parent. Let's see, the parent y equals square root of x. The parent that gives birth to all of these, has these points on it. And so we had the downward shift by 1, 2 units. And then we had the right shift for the replacement of x with x minus 2. Now we've got the multiplication by -1, which is going to result in the reflection through the x-axis, because now we're just like making all the y values. They all used to be positive, right? In the original graph, all these y values like 1 and 2, right? There's the point 42. 2 used to be a y value. Now -2 is a y value, right? Because now you've got the point for -2. And multiplication by 2 stretches the graph vertically by a factor of 2. We can see how stretchy this looks right here. And then we've got a reflection through the y-axis achieved by replacement of x with -x, because now it's the negative values that used to do what the positive values did in the parent. So, in order to get y equals 2, it used to be a +4 for a value of x, but now it's a -4 that you got to put into here for x, so that you could take the negative of it and get 4, the square root of which is 2. And so -4, 2 is on the graph of the reflected version. Another transformation of some interest is taking the absolute value of a function. Y equals absolute f of x. Okay, so you got a function, and then you're like, okay, what if we took the absolute value of it? Then according to the definition of absolute value, y equals f of x when f of x is greater than or equal to 0, and the negative of f of x when f of x is less than 0, right? Absolute value of a number a is a if a is greater than or equal to 0, and negative a if a is less than 0. Well, by that definition, we have this statement. This tells us how to get the graph of y equals absolute value of f of x from the graph of y equals f of x. Okay, so let's say that y equals f of x is the graphs of sine x. Let's just say it's f of x is sine x. Okay, so here's sine. Get this wave going. And now we're going to get the graph of absolute sine x. Okay, so this is sine x, and then we're going to have a graph for absolute sine x. y2, say, is absolute sine x. Okay, so this is how we're going to get it. The part of the graph that lies above the x-axis remains the same. So this is going to be the same, but the part that lies below the x-axis is reflected about the x-axis. And the effect for absolute sine is boing, 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 boing. It's just going to bounce all over, all the way across the x-axis.